Okay, so this is 8-4, and we're talking about multiplicative inverses with matrices now, and we can also look at matrix equations. Now there's some terminology that we can relate to stuff that we already know. For example, multiplicative identity is like the number 1. So if we multiply some number, say 6 by 1, we still get 6. That's what this is right here for matrices. Having 1s down the main diagonal and 0s everywhere else, we still end up getting the same original matrix here. So what that means is that this 1s down the main diagonal and 0s everywhere else, so exactly what it says right here, those are the identity matrices. I can multiply any matrix by this, any 2 by 2 matrix or 3 by 3 matrix by these, and they won't change at all. Now, we can also talk about inverses. So for example, 6 and 1/6, when we multiply them, give us 1. Those are multiplicative inverses. And we can look at the same thing with matrices. So this gets us back to the identity. And we can do the same thing with matrices. A times its inverse is going to give us the identity matrix. So let's go ahead and jump into some examples here. So it says show A and B are multiplicative inverses. So what we need to do then is multiply A times B, and then we also need to multiply B times A. And if both of those are equal to the identity matrix, then that's showing that they are inverses. So let's multiply A times B. And B. And multiplying them, we're going to have -1 times 5, -5, and 3 times 2 is 6. And then down here, 2 times 5 is 10, and then 5 times 2, -10. And then -1 times 3 is -3, 3 times 1 is 3. And then down here, 2 times 3 is 6, and -5 times 1 is -5. So that gives us 1, 0, 0, 1, the identity, which is what we were looking for. And now we just need to check this one, B times A. So we're switching the order here. So 5, 2, 3, 1, -1, 2, 3, -5. And like we said in 8-3, switching the order is going to get you a different answer. The only time that's not true is if they are in fact inverses. So that's an interesting and helpful property of multiplicative inverses. So multiplying 5 times 1 is -5, 3 times 2 is 6, 2 times 1 is -2 plus 2, 5 times 3 is 15, minus 15, and then we have 2 times 3 is 6, and -5, and that again gives us 1, 1, 0, 0. So that means A and B are multiplicative inverses. Okay. This is your answer. Showing the work that they are inverses is what your answer is. So you can't just say this, you need to show it here. Now we can also be given a matrix and find the multiplicative inverse. So we don't know what the multiplicative inverse is. So what we're going to do is we're just going to put variables everywhere. We know it's going to have the same order. And I'm just going to put W, X, Y, Z there. We don't know what it is. But I do know that 2, 5, 1, and 3 times its inverse, W, X, Y, Z, will give me the multiplicative inverse, or multiplicative identity. So what I'm going to do then is I'm going to multiply these out and set each element equal. So if I multiply these, I'll just do that really quickly here. We're going to have 2W plus Y and 5W plus 3Y And then for here, we've got 2 times x and 1 times z. And then we've got 5x plus 3z. And that's equal to 1, 1, 0, 0. And what that means is each specific element is equal. So if this matrix equals this matrix, then 1 is equal to this. And this is equal to this. And this is equal to this. And this is equal to this. So we can set up those equations. Now when I set up these equations, I want to think about the variables. So looking back, thinking about what we were doing in Chapter 7, I want to combine these two equations because they both have w's and both have y's. So I have 2w plus y equals 1, and I have 5w plus 3y equals 0. Okay. Now looking at these two equations, I think it's easier to use substitution. So y is equal to 1 minus 2w, and then we'll plug that in here. And solving here, we end up with w equals 3, and then plugging that back in, y would be equal to 1 minus 2 times 3, negative 5. And then we can do the same thing with these other two equations. So I can set up having 2x plus z is equal to 0, and 5x plus 3z equals 1. And again, I think substitution is going to be best. And so what we can do here is we can set z equal to negative 2x. So z is equal to negative 2x. And solving, we end up with x equals negative 1. And z is equal to 2. Well, we have all of these pieces now. We can go ahead and plug them back in. And we have w, x, y, z. So A inverse is equal to w was 3, x was negative 1, y was negative 5, and z was 2. And that's our answer. Okay, so I'm going to go ahead and flip the page and do some more examples. Before we do a couple more examples, let's talk about some vocabulary here. So a matrix that we can find the inverse for is called an invertible matrix. Means we can find the inverse. They're also called non-singular. Now, singular matrices are matrices where it's not possible to find the inverse. And I just showed you the long way for finding the inverse, but for 2 by 2 matrices, we can find it using this little shortcut here. So this is really just a formula that we can use here and something that you're going to want to know. However, if AD minus B, and then there should also be a C on here, BC is equal to 0, then it does not have a multiplicative inverse. So 1, you want to make sure you change that, and 2, look at this piece of information here. So let's go ahead and do these two examples here. Okay. Now, we're given a matrix. We want to find the inverse. We're going to use that shortcut. And this is my A, B, C, and D. So we're just using that formula. So 1 over, we'll have negative 1 and 4 minus negative 2 and 3. We're just plugging in those values into the formula we have up here. And we're multiplying that times the matrix, 4, 2, negative 3, and negative 1. Now notice this is not the same matrix I have here. Notice that here A and D switch places, and B and C stay where they're at, but they change signs. So that's what we have here. Then I have, this simplifies to 1/2 times 4, negative 3 to negative 1. And that would end up being 2, 1, negative 3 over 2, and negative 1/2. And that's inverse of matrix A. Okay. Looking down at the next example, we can use another method here. We can also use row operations to turn the left side of the matrix. Actually, maybe I'll write this down for you guys. So these are some directions here for another method we can use for finding the inverse. Now, I'm going to show it to you first with an easy 2 by 2 matrix, but the method that I'm describing here will work for any square matrix. So we could have a 3 by 3 or a 4 by 4 and so on. Now, let's go ahead and look at this first example here. So I'm going to set this up using row operations. So I have negative 1, negative 2, 3, 4. We're going to put this line right here, and then I'm going to put the identity matrix. So what I'm describing here is that we can use those row operations from sections 1 and 2 to turn this left side into the identity matrix, and then what's left on the right side will be the inverse. So first thing is I'm going to multiply row 1 by negative 1. And I didn't change row 2 at all. And then my next step is going to be to multiply negative 3 times row 1 and add it to row 2. So when I do that, row 1 did not change. For row 2, this is going to become a 0. Negative 3 times 2 is negative 6, plus 4 is negative 2. And then I'm going to, let's see, that'll be negative 3, 3, and that'll become a 3 right here. And this will stay a 1, and that's where we are. And sometimes it's easier to get a 0 first before we get a 1 here. So I'm just going to add row 2 to row 1. So 0, negative 2, 3, 1, that didn't change. And 1, negative 2 plus 2 is 0, 3 plus 1 is 2, 1 plus 0 is 1. And our last step is going to be negative 1/2 times row 2. So row 1 did not change, 1, 0, 2, 1. And negative 1/2 will make this 0, 1, negative 3 over 2, negative 1 over 2. What that means is that this is the inverse of matrix A. Okay. And we have one more example to get through. I'm going to go ahead and do that in part 2 of this video.